So we just have a couple loose ends to tie up for our electromagnetism unit. And let's talk about transformers. So these are things that are you can find if you have like a power cube that you're plugging in some device. That's what's in there. So let's talk about how that works. So the transformer has something to do with the number of turns, which, as we mentioned, was one of the ingredients in the flux. It's the one we haven't done much with yet. For the most part, we've set it to 1 because we've had just one loop, but now let's play around with the number of turns. Here's what a transformer is basically. What we have is a solenoid, a coil of wire, and I'm going to call this the primary circuit, or P for short. I obviously haven't drawn the whole thing. There's going to be some source where some current might come from, but the current's going to flow around the solenoid. And then there's going to be a second circuit that looks like this. Oops, that's not working at all. Trying to mark where that works. And the coils are going to just be interwoven. Now, they're not actually connected, so you'll have to imagine that there's some insulation on the wires, right? So these are not, this is not one circuit. These are two independent circuits which just happen to share the same physical space, okay? So this is the secondary circuit. They are, again, not electrically connected, so they're not directly in contact via a conducting path. Okay, so the two wires don't touch each other, they're just laying close to each other. Again, if it helps, think of both wires as being insulated so that they can't actually communicate by having a particular electron jump from one to the other. So you may wonder then, well, what would be the purpose of having them right next to each other? If they can't electrically communicate, well, they share the same physical space. And of course, if you send a current through one solenoid, that creates a magnetic field towards core. Well, that's flux that can be caught by the secondary circuit. So they can communicate by magnetism. So primary creates flux, and secondary catches that flux. So what we can do is use Faraday's law to induce a current in the secondary. Okay? So that's how they're going to actually communicate. So the basic principle, again, the concept is that you send current into the primary. That creates a magnetic field in the primary solenoid. And that flux is caught by the secondary. Now, this is where I remind you that Faraday's law is very strict about what can induce current. Just flux isn't enough. Oh, don't walk. Oh. Just walk right across the camera. If you come in late, try to go up the side if that's just less disturbing to everybody. Okay, so Faraday's law is very strict about that flux is not enough. What has to happen with that flux for anything for Faraday's law to kick in? It has to change over time, exactly. So if this flux is changing with time, then we get an EMF that's induced, and that will drive an induced current. So if we want the flux to change with time, what has to be true of the current that's sent into the primary? Can that be constant? No, it can't, right? Because if we sent in a constant current into the primary, that would create a constant magnetic field, that would create a constant flux, and nothing would be induced in the secondary. So it's actually important we need to send a changing current into the primary. So that's where we can take advantage of Faraday's law. So we can actually have that something happens in the secondary which is a completely disconnected electrically, but it's not disconnected magnetically. Okay? So what we're going to do is we're going to send a current in the primary that's going to have to change with time. And if that's the case, if it changes with time, then we can potentially get a current in the secondary which is induced. Okay, so this has to change with time, and then we get the secondary current. Okay, so let's work out the details. Question?
What determines the direction? Is it always, I guess, opposite?
Oh, well, I wasn't trying to necessarily show any relationship here. It depends, of course. If this is increasing, it'll fight that. If this is decreasing, it'll fight that. So, you know, it'll depend on the situation, right? So don't try to associate the directions right at the moment. We can work that out later. Okay. The only thing, of course, we should do is on the one side, we shouldn't draw the current coming in and here, because that doesn't make any sense. It has to go in one way and flow out the other way. Okay, so let's work out the details. So here is our Faraday's law. And one of the things that I'm interested in is the number of turns. And so the other ingredients, let's just leave them in there. I'm going to just pull it out like this. So I'm just going to pull out the number of turns, and then I'm going to put a little subscript reminding me that the rest of it is now the flux change per loop, right? So flux change per loop times loops is total flux change with time, right? So I don't want to mess with the other ingredients. I just want to pull out that ingredient, the number of loops, which is what I'm concerned with, okay? So let me write down that equation for both loops, or for both the primary and secondary. So it would look like this. So in the primary, it would look like this. And in the secondary, I just put down the secondary. So here's the way to think of this equation. Ultimately, the EMF in the primary, that's your source of current. That's what's driving the current in the first place in the primary. Okay, so this is your input. I haven't drawn it, but there is some EMF source. Of course, current doesn't flow into the primary just out of nowhere. I might put that over here. So this is the primary EMF source. And I'm going to draw it as an AC because that's one of the ways that I can very easily make sure that the current always changes with time, right? If it's sloshing back and forth. That way it's always changing. And I'll always have current sloshing in the output, the secondary, to try to fight that change. You would not want to have a DC source here because, of course, that means current would flow one way and it would establish a constant magnetic field, and then we wouldn't get anything in the primary. So it's actually really important that it's an AC source. Okay? So there is going to be an input, the EMF on the input side, the primary side, and that is going to create a flux change per loop in the core of the primary solenoid. So now let's talk about the communication between the two. So here is one loop of the primary. It has current going around like this. It's going to create a magnetic field through its core, which I don't have to draw the whole thing. Just draw a little bit of it. Looks like that. Did I draw it the right? Well, I drew it the wrong way according to the right-hand rule, so I should really pay attention. So that's my, I think that's right, yeah. So I wrap my fingers around the currents, magnetic field through the core goes like that, right? So that's my, I guess I can write, this is my current through my primary, and this is my magnetic field, right? So that is the, just what's made in the primary, but the secondary is right there to catch it. So I can go ahead and draw right next to it. I'll try to draw it as close as I can to the same thing. There is my secondary loop, right? Now, as far as which way does the current get induced in this, well, what do I need to know in order to figure that out?
Magnetic field.
Not only the magnetic field, but what else about that magnetic field?
The direction.
Not only the direction, but also
Size.
I don't actually need to know the size. I need to know what about how that size,
Well, the angle.
is it whether it's increasing or decreasing. That's right? Because remember, if this magnetic field which points downward, if it's increasing, then what's the direction of B induced? It's opposite, right? It wants to fight that change. But if this B is decreasing, then B induced wants to point the same way, right? So let's say, just for the sake of argument, that B happens to be increasing at this moment. Well then, of course, it would want to fight that change. B induced would point this way, and the current would flow the opposite way. That would be the I, and the secondary would go like that. So that's the mechanism by which this works. But what I do want to point out is that because these two, the primary and secondary coils, are basically right on top of each other, what it means is that whatever flux is made by one is exactly caught by the other, right? So one of the things that I can do is realize that this quantity is the same. Okay? So the flux change per loop. This is the flux change that's sent, and this is the flux change that's caught. And we are going to assume that there is a 1-to-1 ratio between the flux that's sent and the flux that's caught per loop. Okay? So if that's the case, then of course, if you're catching flux change per time, this is your output. That's your induced EMF, and that's going to induce the current. So here's what I propose, is that that flux change per loop, if it's the same, let's just eliminate it from the equation, and we have this. Now, just because I eliminated it from the equation doesn't mean it's not hugely important. Remember that if there were no flux change per time, then there would be nothing happening. Okay? So flux change per time is essential. Now, let me solve this for the output. That might be what I'm most interested in. And here's something interesting that you notice is that the output EMF may not be the same as the input EMF because there's this ratio of the number of turns here. So we are not guaranteed to get exactly the same EMF on the secondary output side as the EMF side, and this is why this is called a transformer, is because there's something being transformed. What you get on the way out is not exactly the same as what you put in. So what you have in the front, that multiplier, is a ratio of turns, because you can have more things that send and less things that catch, or vice versa. Basically, now we're comparing the number of pitchers to the number of catchers. Okay? I'll go ahead and go through the permutations of that equation, but before I need to clear some space. Are there any questions on anything I've put up on the board so far? Yeah?
You were saying how you have to have AC, so how does it work like when you have your car adapter to charge your phone that runs from a DC source? Is that a totally different setup, or?
So you're asking like if you plug in like to your car charger, you plug your phone in?
Yeah.
Well, notice that there's no power cube there, right? There's no transformer involved.
Well,
That is,
yeah, I guess that's my question, is what's inside those little things?
oh, what's inside the little like adapters?
Yeah.
I think that's just very simple, like connecting the right thing to the right thing. There's just like connecting the different pin configurations. There's nothing terribly exciting going on in there.
Because your phone's like, what, 5 volts, and then the car is 12, so something's got to, is that just like resistance that brings it down?
Right, so there may be some kind of, so I should mention that transforming is a very specific process. So that may not be what I'm talking about here. There may be some adaptation, but your car battery is DC. Your device normally runs off a battery of another kind, so that's DC. So there's no AC involved there whatsoever, right? So you may need to do something to change the voltage, but you're not changing it from AC to DC or anything like that. There's nothing going on there, okay? Okay, so let me clear some space and go through the permutations here. And here are the different cases. We could have that the number of loops in the secondary is greater than the number of loops in the primary. If that is the case, well, first of all, I guess let me draw it. That would look like this. We'd have less in the primary and more in the secondary. And by the way, I should mention that oftentimes, just so that it's not hard to count the loops, we just kind of bounce them out so we can look at them. For instance, there you can tell there are far more red loops than black loops, right? So here there are more catchers and less senders. So basically, if you have a large number of these catchers, you can basically have that you're kind of getting the same flux that's being sent by one primary loop is caught by more than one secondary. So it's almost like you get to double count your flux. And what that means is that the EMF in the secondary is greater than in the primary. So you can see that if this ratio is greater than 1, you get more EMF on the output than on the input. This is called a step-up transformer because it's stepping up the voltage, it's increasing the voltage. Now this might be a good time to remind you that the units for EMF are joules per coulomb, which is a volt, of course. So we're getting more joules per coulomb. So you might ask, isn't this a violation of energy conservation to get more energy per charge? Where does that more energy per charge come from? Well, obviously we can't just conjure more energy out of nothing. There's something that has to give. I haven't yet told you what it is. But we are increasing the EMF. Basically, we're increasing the voltage. Okay? The other case, of course, is if there are less loops in the secondary than in the primary. So that would look something like this. More senders, less catchers. And in that case, the EMF in the output, the secondary, is smaller than in the primary. So if we've decreased, we call this a step down. So we basically have less voltage on the output. And this might seem more palatable to have less energy per charge. You can just say, oh, okay, I can understand losing energy. Maybe it's lost to heat or something, but there's no resistors here, so where would that mechanism to lose it, where would that be? It's going to turn out in both cases. That's not really the correct analysis. When we increase the voltage, we don't get more energy, and when we decrease it, we don't get less energy. The energy going in and the energy coming out are exactly equal. The energy is just transformed, okay? That's why we call it a transformer. It just changes how the energy is carried. And the key to realize here is that this isn't really joules, it's joules per coulomb. So we do have flexibility on the coulomb side. Here's what happens. The energy going in is exactly equal to the energy going out. If we, for instance, minimize the fact that the wires themselves always have a little tiny bit of resistance, but if we neglect that, we should expect that the energy going in is exactly the same as the energy going out because there's nowhere to lose it. Well, we usually, of course, talk about rates. So we expect that the energy going in per time is equal to the energy going out per time. So basically we gave a name for energy per time, that's power. So we expect that the power input into the primary is exactly equal to the power output in the secondary. So let's talk about what would be an appropriate form for the energy. Here's my suggestion. If you want to calculate the energy per time in an electrical flow, you multiply the current by the EMF. Okay? Let me explain to you why that is a good measure of how much energy is carried in the electrical flow. What's the units of current again? Amps, which is short for what? Coulombs per second. Or more generically, charge per time, right? It's the flow of charge. And then what's EMF or voltage? I just told you. That, of course, is joules per coulomb, or energy per charge, right? How much energy is carried in one charge. So the charge is really the middleman, of course. That's where the energy is carried. Those are like the mail carriers for energy. But I can cancel that out, and what do I get? Of course, I get energy per time. So the energy carried per time in electrical flow is just basically first asking how much energy does each carrier, each charge have, and then how many charges do you get per time, right? By the way, this isn't entirely unfamiliar. One of our equations for a resistor was P equals IV, right? It's basically the same deal, except for this was energy loss, right? We're losing energy to the environment as heat. So here we're not necessarily losing it to the environment, but we can still talk about the energy that's carried along in a charge, okay? So if I have to make sure the energy is all there, I might write this. I'll put in the same formula on both sides. And of course, what that then means is, if you increase one thing, it's at the expense of the other. So if, for instance, you have a higher EMF in the secondary, you must have a lower current, right? So if we go over to the step up and step down, and by the way, the step up and step down is always relative to EMF. It tells you if the EMF is stepped up or the EMF is stepped down. And because the reason I mention that is because whatever is happening with the voltage, the current is the opposite. So what's happening here is that the current is actually decreasing. So the current in the secondary is smaller. And vice versa over here in the step down. If you step down the voltage, then the current will increase. Okay? That's what makes sure that the energy is always there. So here's what we'll find, is that if you step up the energy per charge, you'll have less charges, right? So it might look something like this. If you have a bunch of charges flowing in here, you'll have far fewer flowing here. If you go to more energy per charge, you'll have less charge per time, okay? So I kind of refer to this as the capitalist direction, capitalist, where what you are doing is you're transforming the energy such that there is more energy per charge, but less charges per time. You're giving the energy to very few charges, each of which carry a lot of energy, right? So it's like very few people having very much money, right? The 1% crowd, right? So that's what you are doing when you send electricity through a step-up transformer. You are taking the energy and you are giving it to less charges, each of which carry more energy per charge, okay? And vice versa, when you go through a step-down transformer, you can kind of call that the communist approach, where it's the opposite. You go to less voltage, which is less energy per charge. So now you are sharing the wealth, okay? There's less energy carried by any one charge, but you have more of them. So you have more charges per time. More charge per time. So that might look something like this. If you send in this current in the primary, now what you've done is you've given that same energy to a tremendous large number of charges, and therefore each one has less, okay? So it's like spreading butter on toast, right? You're taking the butter and spreading it out so it's not that much in any one place, okay? So it's kind of a neat way to just transform how the energy is carried. The energy, it's like a parlor trick for taking the same amount of energy and just transforming how it's carried, either giving that energy to more charges, which get less energy therefore, let's step down, or you could take that same energy, give it to only a few charges, each of which have a lot of it, okay? Now you might say that's a nice parlor trick, like what's this for? Why would you want to do this? Why would you want to take the same amount of energy that you already have and just, change how many charges carry it versus how much they each have? Well, this is the backbone for our electricity transmission system, okay? So this is going to turn out to be indispensable for how to get energy from one place to another. So that's the thing I want to talk about next. Are there any questions before I do that on just the basics of what step up and step down do? Okay, so let's talk about getting energy from one place to another. So over here, we have some power plant. Perhaps it's a coal-burning plant. Probably don't want to live in that building or near that building. So you live over here. Well, we talked about electricity generation. How is it generated? But then once that energy is transformed from some other form into electricity, we need to, of course, get it to you. So we put in some kind of power line. So maybe it's on some poles where you can see it. Maybe it's buried underground, right? So here's the thing to realize is that that power line no matter what you do, is going to have some resistance, right? We haven't yet figured out how to make room temperature superconductors, but once they do, that'll be a revolutionary technology to the entire world. There will be some resistance, and obviously there isn't just one resistor that they put in the middle there. The whole thing has resistance, but I'm just representing it right here. Okay? So what's going to happen? Well, we know from our studies earlier, homework 3 and such, that first of all, there's going to be some energy loss. And we, of course, have several different power laws to choose from. But this one, I think, is the easiest because the voltage is, of course, going to continuously drop, because if there's continuous resistance all along the way, the voltage is going to gradually drop. But I can at least be sure that the current that gets sent in one end is the current that's going to come out the other, right? I could also, of course, talk about Ohm's law over the length of the whole thing. It's going to be V equals IR. And of course, this is my chance to remind you again that this is delta V. So it represents the voltage difference from one end of the wire to the other, right? So what happens is, as you encounter more and more resistance, you can kind of imagine this as a, if you want, as a very, very long chain of series resistors. The voltage is going to drop the whole way, right? So if the charge, say, is moving this way, we know the current is the flow of positive charge, so the end will be at a lower voltage than the beginning. Of course, that's the only way that charges would want to burrow through any kind of resistance, is they have a reward, right? And that reward for positive charges is lower voltage, right? Okay, so let's try to minimize our power loss, because this is wasted energy, right? Once you make it, why would you just want to sweat it out to the environment along the transmission route? You want to get the energy to the consumer, right? If any losses are incurred, guess who's paying for it? You are, right? So we want to minimize the power loss, right? So we want to minimize the power loss. Well, we only have two choices of how to do that. We can talk about minimizing I, and we can talk about minimizing R, right? So let's take a look at both approaches. Let's try to minimize the resistance. I'll call this the Edison approach. And let me talk about minimizing the current, which is going to be what I'll call the Tesla approach. So, let's see what we can do about resistance. Well, this is where I can remind you what are the ingredients to resistance. Resistance is equal to rho L over A. So the factors are the resistivity of the material, the length of the resistor, and the cross-sectional area. So, first of all, what do we want to do with the resistivity? Do we want low resistivity or high resistivity? We want low resistivity, right? That will make sure that the resistance is as low as possible. Okay, let me not put anything in that space right there. Okay, so let's make our power lines out of, say, some metal instead of some horribly unconductive material, right? But we also might find some really esoteric material that has an even lower resistivity than, say, copper, but it might be really expensive, right? So we want to have the lowest resistivity that can reasonably be used, right? So there are limitations here in terms of material, finding things that have low resistivity, and of course, not only if those materials exist with that lower resistivity, but how much do they cost? Okay? All right? So let's take a look at the cross-sectional area. What do we want to do with the cross-sectional area to lower the resistance? Increase it, right? We want to make it a wide tube, so to speak, right? Have a large cross-sectional area so charges can kind of get through side by side. What's the problem with increasing the cross-sectional area? It'd be heavy and expensive because you're using more material, right? So what are the limitations on this one? Weight and cost. There's only so much you can do on that. Okay, what should we do to the length of the thing? Decrease. We want to make it as low as possible. This one has a really obvious limitation. What happens if it's too short?
Doesn't get to you.
It won't reach. Okay? That's a big problem. So, the solution posed by Edison, by the way, was, well, okay, we can't make these power lines very long, which means that everyone is going to have to live within about 10 miles of where their electricity is generated. Because otherwise, the length of the power line would be too long, and the resistivity, or the resistance would be too high, and you'd have too much power loss and too much voltage drop across the end, okay? You'd lose, if you, for instance, generated 100 volts here, you'd have, what, like 2 volts left. You drop the voltage so much. So he was fine with that. Okay, well, he owned the patents for many of the things in the power plant, so it was very much in his financial advantage to build one of these 10 miles from everybody's house. He stood to become very wealthy. Okay? Now, let's look at some alternatives. Well, there's only so much you can do on the resistance side. Hopefully I've conveyed that to you. Let's see what we can do with the current side. Let's see what we can do to make the current low. Well, we have just arrived at a device which can manipulate the current. So what we might do, once we generate the electricity, is we can put in a step-up transformer. A step-up transformer, remember, it steps up the voltage. It goes to high voltage. You may have heard of high voltage power lines, right? Why are they high voltage? They're high voltage because they're low current. The whole purpose of a step-up transformer is you go to more voltage, less current. So, how are we going to get the current smaller, right? We use a step-up transformer. Step up, it goes to higher voltage, and we can go to lower current. And there's no impediment to that except for just making sure that the ratio of turns is correct. Okay? So, notice, by the way, though, is that the transformer, its whole operating principle is that the current has to be changing in the primary in order for the induced current to come out of the secondary. So really what we're talking about here is the argument is between AC and DC. Okay? So the transformer is this parlor trick, but it only works if you are willing to have the current be AC. So remember, we talked about very naturally it gets generated as AC. You go straight into a transformer, you can step up the voltage, step down the current, but it's all working off the fact that the current is sloshing back and forth. It does not work over here, right? If you just sent in a constant current into a transformer, you would not get any current out of the secondary. You don't have the ability to use a transformer if your current is not sloshing and changing all the time, okay? So what we're talking about here is the argument of how we're going to structure the electricity grid in America. So here's the thing. Edison famous for inventing things like the light bulb, right? He was not a mathematician. His whole strategy was just try, make 100 prototypes and trial and error, and hopefully you'll get something. Okay? Because he didn't have a lot of training, DC was something that he understood. It's, of course, what we focus on in this class because it's easier mathematically. We've just barely touched upon AC because once you start to have sine functions and stuff like that involved, it gets much more complicated. So in we have Tesla. Tesla has the mathematical training so that he can calculate in AC. Okay? So this is the argument we're faced with. And we arrive at something called the war of the currents. Now at this point, I have probably convinced you that the transformer is an indispensable tool for manipulating electricity. But the odds were stacked definitely in the other direction. Edison was already very famous, and Tesla basically arrived in America with basically nothing, begged Edison for a job as an apprentice. I think he spent some time digging graves and then finally got an internship with Edison. And Tesla tried to convince Edison that AC was the future. Edison was not listening. It was beyond his mathematical training. Edison was not university trained. Tesla was. So eventually, Tesla quit, found himself a wealthy backer, George Westinghouse. You may have heard of Westinghouse. And off went the war of the currents. Okay? They were both trying to convince the public that the other's electricity was dangerous and should not be used. Okay? So DC, this was not yet available in everybody's house or anything like that. One of the few places where they had DC already, if there's going to be one place that gets electricity first, New York City. So they had DC. It was a good place to have it because if you have a power plant, it needs to be within 10 miles of everybody's house in New York City. That can service a lot of people, right? To avoid the massive voltage drop that they would get from one end of the wire to the other, the solution was just have the voltage be super high so that when it drops a little bit upon arrival, it's still high enough to be used. So one of the things that they first electrified was the subway cars. So the your rail in your subway car where it gets its electricity, right? And it was at such high voltage that occasionally you would have a dielectric breakdown. We learned that you get to a high enough voltage, right? You get your electric field past the dielectric strength of air, and you get lightning, right? So people would be walking along trying to get their subway car, whatever, and it just gets zapped. And so these people in Brooklyn would get this nickname because they'd always be dodging these high voltage arcs. They call them Dodgers, the Brooklyn Dodgers. That's where they got their name. They've since moved to LA. Okay. So obviously this is not the way to go. So as you can probably guess, Tesla won this eventually because we don't have a power plant within 10 miles of your house. You can get electricity from hundreds and hundreds of miles away. In fact, the whole idea of the electricity grid is that there are a large number of generation plants everywhere, and then the electricity grid manages where the production is, where the demand is. You can be getting your electricity from hundreds and hundreds of miles away. And you can be doing that with very minimal energy loss in transit because of the transformer. Okay? So this war of the currents, it was vicious, but of course, good technology always wins. I should mention in the process, one of the more kind of sucky things that Edison did, to try to prove how dangerous AC was, he invented the electric chair. So he said, look at how dangerous AC is. You can electrocute someone with this and prisoner was executed using AC. Now, don't get me wrong, they're both dangerous in everyday, the amounts that we tend to use. It's just a matter of course, using it responsibly, okay? So the big triumph of AC was when they put an electric generator in under Niagara Falls. And so they, of course, put in the generator in Niagara Falls, which is hundreds and hundreds of miles away, and then lights turned on in New York City, and pretty much from there was no looking back. AC was going to end up being how this country was electrified. Now you can go to a rural area which is hundreds of miles away from any kind of power plant, and you can reasonably expect they might have electricity, which would not have been possible if we had gone with DC. Okay? So this is what we use today. I posted, I think, some links where you can read more about the War of the Currents. Okay? One of the interesting things I always find is that during the middle of the War of the Currents, George Westinghouse, when they were kind of installing all this stuff under Niagara Falls and everything like that, he went to Tesla and said, look, we're running out of money. Tesla basically single-handedly came up with many of the elements in our modern electricity transmission system. He just dreamed them up, put them on paper, and everybody today uses that technology that he single-handedly thought of. If he had kept the patents for all that stuff, he would have been the richest man in history. But he tore them up, and he actually died penniless. But his gift to the world was the fact that this stuff that he personally thought of, we all use it constantly. Okay? So what we have around today is AC. We've only briefly touched upon this because it is mathematically more challenging to deal with, this constant sloshing back and forth. But hopefully you can see it is more natural to generate it that way. You're able to transform it, and you can also actually use it that way. So when you plug into an electrical outlet, it's AC. It sloshes back and forth from one prong to the other. For most applications, it doesn't matter. For instance, if you're running it through a toaster and you just want to make heat out of it, does it really matter if it's sloshing back and forth? It still generates heat going both ways. Okay. So that's a bit about the transformer. Are there any questions on that? Yeah.
Just to be clear, when you put alternating current into a transformer, alternating current comes out.
Correct. So if it sloshes back and forth on the input, it sloshes back and forth on the output, because of course the induced current is constantly trying to fight the flux change. I should mention, of course, as well, you're stepping it up. It's high voltage. It might be in the kilovolt range. High voltage power lines are low current power lines. But then you step it down when it arrives. You don't need to be at 10,000, 20,000 volts once it arrives. This actually gets taken care of in a series of steps. So you may have a regional transformer. Okay. Have you ever walked by a lot with just kind of some metal towers and these kind of weird cone-looking things? It's a transformer substation.
Well, got knocked down.
What's that?
Didn't it get knocked down by Burlingame like a couple weeks ago?
That's very, very possible. Yeah, they do go out from time to time. Sometimes it's just wind knocks them down. Sometimes people. I heard somewhere in the peninsula someone was sabotaging one that fired shots into a transformer substation and knocked it out. There's a series of kind of regional step down. There's even one that right before it goes into your building, there's a transformer. Usually they're buried, and I once had an apartment where you look out the window and you can see it right there, like right on the corner. And it eventually steps down to 120 volts. Okay, so that's what you get out of your power outlet. And if that's exactly what you need in your device, then you just plug it in with an electrical cord that has, it's just a piece of conductor. But you may want to step it up or down further from that. For instance, those old CRT TVs that no one has anymore, those stepped it back up to, I think, several thousand volts. That's why you want to really be careful reaching in and touching, especially even if it's unplugged. It may have a large capacitor that's charged up to that voltage. Those power cubes that you have, those are transformers which step it up or down further. Usually they'll step it down to 9 volts, or oftentimes I should say. And the reason is, why would you want to step it down to 9 volts? Well, usually that's a power adapter for something that normally runs off a 9-volt battery. So you don't really want to be connecting it when you plug it in to 120 volts. You fry it, right? So what it does is it steps it down to the voltage that it natively likes to use when you're plugging in a 9-volt battery, right? The other thing that it can do is it can take it from AC to DC. So that's a process called rectification, where you take the sloshing back and forth and you make it all go in the same direction. And the reason, of course, is you're trying to simulate what it normally gets when a battery is connected, right? The easiest way to do what's called this, so in addition to the step down, there's a separate thing that it does called rectification. And just to simplify that process, if you take a current that's sloshing back and forth, and you just block it when it's sloshing one way, right? So you only let it in when it's going one direction, and when it tries to slosh back the other way, you block it. So then you kind of get this thing that just spurts in a single direction. That's direct current. Of course, it's direct current that is going to be changing its size. All you do is you throw in a capacitor, right? Capacitor will charge up. If you want to charge it up in spurts, that's fine, but on the other end, it releases the current in a smooth manner. So that's how you take something that looks like this, current versus time. It sloshes back and forth. First thing you do is you cut out the peaks that are sloshing the way you don't want, and then you use a capacitor to smooth it out. So that's how you get from AC to DC, if that's what you want, okay? So just because you commit to transmitting, just because you commit to generating and transmitting the electricity in AC doesn't mean that you can't have it as DC if you want, okay? So that's what those power cubes are, and they often have a lot of weight to them because they're just basically a bunch of turns in there, and so, of course, that's metal, it carries some weight to it. Question?
How do you go the other way?
Right, so I don't want to get into how that works, but it's possible to reverse it as well. That's something called an inverter. So if you're interested, you can look it up. So inverting is going from DC back to AC. Okay, so that's a bit about transformers. You can see that it gives you this immense power to manipulate electricity, right? You can change it to whatever voltage you want, as long as you have the transformer to step it up or down to that. Question?
How do you change the voltage? Is it by changing the number of loops?
That's right, so you just manipulate this ratio. Then you can manipulate what is the voltage coming out of the secondary versus what goes on in the primary. So the idea being is if you want to change the voltage by a factor of 1,000, this factor is going to have to be 1,000. So that means that you're going to have to reasonably have a large number of turns if you're going to have one have 1,000 to 1 ratio more than the other, and they are all in the same space. So that's where the weight of the power cubes often comes from. Okay, so that's transformers. And I also just want to tie up some loose ends before we call it a day on homework 7 and exam 2. I want to talk about a couple other things, one of which is the Hall effect. And what the Hall effect is for is to resolve something that we have, of course, been kind of not talking about too much. Now, we, of course, talked about the fact that if you have a higher voltage, and a lower voltage end to a, this is a wire, we of course have conveniently pretended that it's the motion of positive charges to lower voltage. In fact, that's the direction of the electrical current. But we occasionally acknowledge the fact that that's not really what's going on at all, right? It's really electrons going to higher voltage. And we have said numerous times that nothing that we have done would require us to make this distinction, right? So we pretend that current flows to lower voltage, if current is positive charges flowing to lower voltage, even though it's really the other way, because in most applications it doesn't matter. So the Hall effect is the one experiment where we can finally figure out what's really going on. Is it positive charges flowing to lower voltage, or is it negative charges flowing to higher voltage? So we really have to concoct an experiment that's very specific in order to have any difference, measurable difference, in which one is it. So that's what the Hall effect is for. The Hall effect helps us to determine the actual motion of charge in a system. So there will be some measurable different result, and that's how we can use to figure out what we can do to figure out what's going on. Here's my system. My wire here, I'm going to make it just kind of a flat plate, so it has some width to it. And I'm going to hook it up to a battery. Let's make sure the higher voltage end is on the same side as I drew it in the previous diagram. So what's going to happen here is that positive charges are going to flow here. In our usual assumption, they're going to flow from left to right. So they're just going to flow down the middle of this plate. There will be no reason for them to deflect to one edge or the other. They're just going to flow right down the middle, because the left side is the higher voltage and the right side is the lower voltage. But here's what I'm going to do. I'm going to now apply a magnetic field. So everywhere in this region, I'm going to apply a magnetic field into the page. So now let me do my slap rule. I'm going to slap I into B, and the force is up. So what that's going to do is it's going to drag those positive charges, which would normally flow right down the center of this plate, and it's going to deflect them over to here. So they're going to kind of flow like this before they, of course, exit. So they're going to, we're going to find that there's positive charge more toward the top side. Now this is my opportunity to remind you that anytime we have a wire or anything where current is flowing, we assume that that thing is neutral. So yes, there are charges that are moving, but they're moving against the background of the other type of charge, which is stationary. And so we are forced to then conclude that the bottom will end up being a little more negative charged if this whole thing is going to end up being neutral. So if the positive charges choose to flow more across the top, then the bottom will be seen as more minus. So this whole plate should still be neutral, but now we should see, in some sense, it's like there's charge polarization, right? So we do not expect to find an equal distribution of plus and minus charges everywhere. We expect to find more plus on the top and more minus on the bottom, right? So if that's the case, we can take a voltmeter, a very sensitive one, because it's a subtle effect, and we can connect it in this unusual way. Normally we would connect it from between the left and right ends to measure the voltage drop created by the battery. So if this is a 9-volt battery, we'd get 9 volts, and this is 9 volts higher than this, right? But I'm not going to connect the voltmeter like that. That's not the interesting part here. I'm going to connect it laterally. So I'm going to measure the voltage difference between here and here. So the lateral, I'm going to measure the lateral voltage difference. I wouldn't get anything there if I didn't apply that magnetic field, but that magnetic field is going to cause me to think that the higher, so this plus, which is going to be the higher voltage side, the top or the bottom? The top. So we expect that the top is the higher voltage versus the bottom, okay? So don't get me wrong, there's still a voltage difference between the left and right sides, right? If this is a 9-volt battery, it'll be 9 volts here and higher than here. But as we progress from 9 volt to over that drop, we're going to find that at any given place along the way, the top is slightly higher voltage than the bottom, okay? Does that sort of make sense? So in addition to the major overarching voltage drop from left to right, there will always be, at any given point, laterally, a slight voltage difference between the top and the bottom. So this is assuming, of course, that our charge carriers are positive. Now let's go back and do the same setup, but, of course, putting in negative charges flowing the other way. So everything else is still going to be the same about our setup. Same battery hookup, same magnetic field applied externally. But now I'm going to go and I'm going to say, what if it was negative charges flowing to higher voltage? So let's do the slap rule again. So we point, our charge is moving to the left, we slap it into B, force is down, and then what next? It's a negative charge, so the force is actually up. So this has the force as being up, and so these electrons will be dragged up across the top, and of course, eventually they will flow into the other side, but they will be dragged across one side, and of course that will leave a preponderance of protons, fixed protons, more on the bottom, right? So we find basically the presence of the magnetic field will mean that rather than the plus and minus charges all being interspersed, it's kind of like charge polarization, right? The magnetic field causes the charges to drag across one edge of the plate on their way to where they want to go, right? So now let me apply a again, measure the voltage difference. Which side of the plate is the higher voltage now? It's the bottom. The bottom is plus now, so the bottom is higher voltage. We get a different result. So we finally have figured out some way to get there to be a measurable difference between whether or not it's positive charges flowing to lower voltage or negative charges flowing to higher voltage. So, of course, once someone figured out that this would be the case, you get really excited, you run to the lab. Because at that point they didn't know, really, what was the direction of the flow, right? So what do you think you get when you actually go in the lab? When you set these up in this configuration, do you think you'd measure the top as being the higher voltage or the bottom? The bottom. This is what actually happens. So this is an experiment that can actually tell you, and you can believe, they were a bit disappointed to find out that, of course, it wasn't what they had thought all along, right? They'd set up all their conventions around this, and you can imagine their disappointment when what they thought was flowing this way was actually flowing this way. Well, that's when you assign the electron the minus sign so that you don't have to go back and reimagine everything. So we still pretend in nearly every homework problem that current is made out of positive charges flowing to lower voltage, even though it's really not. And this is one of the few things that we can actually figure out there's a difference. That's what the Hall effect is for. Okay? Are there any questions on that? Okay, so that's a little bit about the Hall effect. In some ways, it's almost like a velocity selector, right? Or like charge polarization. It's hopefully not entirely unfamiliar. It's just a new context of that. And then the last thing I want to talk about, I want to go back to your E over M lab. So hopefully you guys remember the general gist of this lab. You had a filament that you heated up. It spit off electrons. They basically got spit off at 0 velocity. And then you applied something called an electron gun. This was an electron gun, which is basically just a region of voltage difference. Basically, you had this mesh. I'll tell you what was in there. There's this kind of mesh grid, which is put at a high voltage. I think it was several hundred volts. And of course, electrons really like to go to higher voltage. So they go, I want to get over there. It has a hole in it, so of course they can slip through. And you can get that there is these of course will have now some final speed, so and so many meters per second, which you can control with the electron gun. Then they go into a region of magnetic field, where of course they curve, right? And you guys got to see them curve into circles, and hopefully got a chance to see the helices curving in both ways as well. But then, for the most part, you used the circle, right? And you had good old R equals mv over qv, right? And so you can control for the speed. You can make that fixed. The voltage difference in the electron gun basically determines the ejection velocity. You can control the magnetic field. And that, of course, is going to, in the case of an electron, the charge over mass is fixed. So you pretty much have a radius that they all make. And you probably saw that, is that they tended to nicely follow a circle, right? It's not like you got them spraying everywhere, hopefully. Okay? The only reason your beam has any width is because some of the electrons come out a little slower or hit a few more air molecules or a few more gas molecules in there. But basically, you got a nice steady stream. Now, let me propose another use for it, some other uses for this. Instead of just electrons, this could be an ion, which is, of course, an atom with an imbalanced charge. So let me say that this is an ion with a charge of, so let's say it has a, it'll have a charge of 1 electron if 1 electron is missing, or it'll have, maybe it has 1 electron extra or something, right? So ions can have electrical charge because they have an imbalance of protons and electrons, right? So let me send some ions in here, some singly charged ions. So singly charged ions. They either have 1 extra or 1 fewer electron or something like that. So this will be fixed as well, but then the only ingredient is what is the mass of the ion, right? Maybe it's a singly ionized, say, lithium versus, I'm just looking at the periodic table, versus silver, right? Well, these are all different things at different mass. So the mass will solely determine the radius. So what I can do over here is I can put little catching bins, knowing that the more mass something has, the more gradual a circle it will make. So I can put these little catcher bins here. This will be the lower mass things that will make a smaller circle, and this will be the higher mass things, higher mass. So the further away you put the bin, the more mass it is. So here's what you can do. You can take a sample, some kind of chemical sample, and you want to know what's in it. So first things you can do is you can take the entire sample, which is a solid, and get it to it's all a gas, right? So all the different atoms that are in it are flying around independently. and then figure out a way, I'm not going to talk about how, but ionize them. And then you run them through here, and then you get a plot of what exactly comes out. You basically do a graph of your bin versus how much arrived in it, and you get this little radius, look like this, and you get a sense of how much mass fell in each bin. Can anyone tell me what this thing is?
Yeah.
That's a mass spectrometer, exactly. Mass spectrometer. And then, of course, you are a detective. You work backwards and say, okay, well, I have, I seem to have a bunch of oxygen and twice as much hydrogen. That's probably water, right? H2O. Okay. So you can have some detective work, and by knowing how much mass landed in what bins, you know what atoms are present and in what proportions, and you can kind of work backward to what this sample was made out of. So that's a very useful and obviously application of this. I'll show you another one. Let's talk about, in the next 2 minutes, let's talk about nuclear weapons. Okay? So uranium, you can dig it out of the ground. There are 2 isotopes of it. Well, there's 2 main ones. There are other ones. Uranium-235 and 238. Now, uranium is actually element number 92. The number here refers to the number of neutrons. So this is 3 more neutrons. Now let me tell you something about what neutrons are for if you don't already know. You may have wondered early in the class, how does anything ever stay together if it's not hydrogen? Because if you go to any other element, there's multiple protons in the nucleus. And we know that protons repel. Here's an interesting fact about protons though. If you have 2 protons, if you shove them together, they will tremendously repel until they will actually stick if you get them close enough. Okay? So despite the tremendous electrical repulsion, if you can get them close enough, they actually stick. They stick because there's an extremely short-range force called the strong nuclear force. So strong nuclear force. If you can get them close enough, that takes over because it's much stronger than the electrical force of attraction, but it's extremely short range. So here, the nuclear force goes to 0 because they're too far apart. So it takes a tremendous amount of force to get them close enough to have the nuclear force take over. All right? So in any nucleus, there is a tension between wanting to fly apart because of the electrical force and wanting to stay together because of strong nuclear force. So there's this tension, and if it's thrown too much on the side of the electrical force, it'll fly apart. But if the nuclear force can continue to hold it together, you have a stable atom. Now the beauty of neutrons is neutrons participate in this strong nuclear force. So they're kind of like the peacemakers. In a nucleus, they allow you to have protons which are a little further apart, right? So it's like, when you have 2 kids and they don't like each other, you have to put in a 3rd kid that they both like, and then it'll kind of won't blow up in your face, okay? So neutrons don't participate at all in electrical force, so we haven't mentioned nothing about them for the whole course. But they do participate in the nuclear force. So neutrons have a calming effect on the nucleus. And having 3 more of them means that this is going to be stable. Okay? It's not going to be something where the nucleus can actually fall apart. And it turns out when the nucleus falls apart, we have something called nuclear fission. And you have potentially that energy release, famous equation E equals mc squared. You get a tremendous amount of energy release. You can do that in a control wave for nuclear power. You can do it all at once for a nuclear weapon. But when you dig uranium out of the ground, I think it's about 98% of this stable kind and less than 1% of this kind, which doesn't have 3 of these peacemakers this is what you want. And you have to figure out some way of sorting out, atom by atom, the good stuff, quote unquote, the good stuff, this with this. This is a process called enrichment. You may have heard of that, you read about it in the news, right? Nuclear enrichment. It's a way of sorting out a naturally occurring lump of uranium. By the way, uranium is everywhere in the world pretty much. You can't guard it. Everybody just has it in the ground. There's nothing you can do to stop them from getting a hold of it. But luckily, enrichment is a very, very intensive process. Okay? So how would you sift these out? You could run them through a device like this. You figure out a way to make it uranium gas. I think you combine it with fluoride. It's like uranium hexafluoride or something. You run it through here. The uranium-235 is of lower mass, and the uranium-238 is of higher mass. It's a very slight difference, so you might have to run it through multiple times. That's why it's called enrichment, right? You might get some of the good stuff in the bad bin, because there's just some kind of spillage. And then you run it through that process a number of times until you have a pure sample, or a much more pure sample of this. Okay? This is not just a theoretical thing. This was during World War II. This device was developed. It's called the Calutron. Cal is for Berkeley. This was just right over the Bay Bridge in the basement somewhere in University of California, Berkeley. And they enriched the uranium used in the nuclear bomb that was dropped on Hiroshima during World War II, partially using this device. They've since figured out better methods of enrichment, but this is one way to do it. So that's a little bit about how this ties into geopolitics, stuff like that. Enrichment, that's why it's such a big deal. You can't protect someone getting a hold of uranium, but luckily it takes usually governmental agencies, a massive operation that's hard to hide before you can enrich this stuff. What we're more concerned about in today's geopolitics is not that, say, ISIS would develop an enrichment facility. They couldn't hide it. I'm sure we'd bomb it right away. But they can get a hold of some that has already been enriched. They can get a hold of a nuclear weapon that someone already made. There's thousands of these from the Cold War, and the only thing that has to happen is for someone to get a hold of something that's already been made. Okay? All right, so on that grim note, that's the cutoff for homework 7 and exam 2. We'll pick up new stuff next time.